Part C, Part C of Module 1. Solve PDEs like ODEs. Yeah. So this semester, I plan to do in this way. We have total 5 modules. In each module, I plan to use one part to talk about PDEs. Yeah. One of the 5 parts. Yeah. So each module, typically, I have 5 parts, A, B, C, D, E. So one of the 5 parts, I talk about PDEs. Yeah. So this is the first one. First one, basically, I give you the, background information. Yeah. Some simplest, basic information of PDEs, partial derivatives. All right. Yeah. C.1, definition of partial derivatives. Yeah. So we just use the derivative, ordinary derivative, to help us understand partial derivatives. Yeah. The ordinary derivative, f function derivative at a point A, it's meaning the rate of change of f function at this point. Yeah. Now, when we move to partial derivatives, we can do the similar way. Yeah. Now we consider functions with 2 or more variables. Yeah. All right. Yeah. So in this class, I only want to consider these 2 cases, the 2-variable function case and the 3-variable function case. Yeah. Yeah. All right. Now, definition of partial derivatives. The rates of change with respect to each variable, yeah, separately. Yeah. All right. Yeah. Let's look at a simple example. If z equals f of x and y, it has 2 partial derivatives. Yeah. F sub x and f sub y. Yeah. We can use this partial notation. Yeah. Partial f over partial x. Yeah. Or another. Yeah. Sometimes we use this notation. Sometimes we use this notation. Okay. All right. And the specific definition, the limit way, similar from the ordinary derivative, but here we consider the partial derivative at one fixed point. Yeah. 1 point. Yeah. But 1 point we use A and B. So here you can see we do not treat A and B as variables. Yeah. We treat A and B as 1 point, yeah, coordinates of 1 point. Yeah. All right. So the definition, yeah. Yeah. The partial derivative with respect to the first variable, we use the similar definition of the ordinary derivative. Yeah. Here you can see the second variable here we just treat as a constant. That b is a constant. Okay? We only treat the first variable. Yeah. So we change that. Change the first variable part. Second variable we never change. When we take the limit, we do not change the second variable part. Yeah. So that's the first partial derivative. Similarly, for the second partial derivative, so we do the similar things on the second variable. Yeah. So that's the, review. Yeah. So I think you saw this before. Yeah. All right. Then partial derivatives are computed just like ordinary derivatives in one variable with this difference. Okay. To compute f sub x, we treat y as constant. Yeah. You do not treat y as variable. Yeah. Treat y as constant. Yeah. Adapt your view to this special way. Yeah. Similarly, when you compute f sub y, you treat x as constant. then it's just like ordinary derivatives. Yeah. The same way as you calculate ordinary derivatives. But this view, yeah, remember this view. But this view, you treat different variables as constant. Yeah. Yeah. Sometimes you treat as constant. Sometimes you treat as variable. So do not get yourselves confused. Yeah. This place, you treat y as constant. But this place, you treat y as variable. Yeah. Yeah. So you need to, so that's the relatively hard part. In the ordinary derivative case, you never need to worry about this. Yeah. But for the partial derivative situation, you need to worry about. Yeah. Sometimes this is constant, sometimes that is constant. You know. Yeah. All right. C.2, chain rule in partial derivatives. Yeah. The chain rule. Yeah. Let's look at the partial derivative version of chain rule. Yeah. Yeah. Many of our calculations, we need to use chain rule. So we need to review this chain rule. The general differential rules. There are many differential rules, right, in ordinary derivatives. Yeah. So you can get similar versions. Yeah. But here we just look at the chain rule. Yeah. Other rules, similar. So yeah, we do not do here. Right? All of the differential rules from calculus of one variable are valid for partial derivatives. Yeah. The high level, yeah. Yeah. So we do not need to rewrite them. Okay? Yeah. All right. But here, we just look at the chain rule. We consider simple case, the simplest case for the chain rule. F of x and y, two variable function, has a special form. There is a capital F function. Capital F function is a one variable function. So here we consider the special form. We want to see in this special form what is the chain rule form. Yeah. All right. But this u variable equals g function, the two variable g function, g of x and y. Yeah. So let's look at the chain rule of partial derivatives, the specific form. All right. Yeah. F, capital F function is a differentiable function. Okay? Differentiable function. All right. Now chain rule. Partial f over partial x. The chain rule. The first part, f, capital F is a one variable function. So we take a df over du, the derivative of f function with respect to u variable. The first part of the chain rule. The second part, u we take the partial derivative, partial u over partial x. That's the chain rule version of that simple case, this case. Only if it is this case, we can do that. If it's not this case, then you cannot get this form. Yeah. All right. Partial f over partial y equals df over dt times partial u over partial y. Chain rule. So you can write these two partial derivatives using the chain rule. Now, the simplest form, case. All right. The first one. Now, second version, we consider another case. This time, a little more complex. Yeah. The second one is a three variable function, f function. Three variable. And each variable is another two variable function. Yeah. Composite. Yeah. Because chain rule. Only when we take the derivative of a composite function, we apply the chain rule. Here, also composite function. But a little more complicated. 3 variables in the original function, but each variable composite, right? Each variable is another 2 variable function with a new variable s and t, 2 variables. In this situation, we want to take the partial derivative. Partial derivative. All right, yeah, because if you look at the function in this form, eventually this whole function has 2 variables, right? S and t, 2 variables. Now we want to take the 2 partial derivatives. The partial derivative of this whole function with respect to s variable, and the partial derivative of this whole function with respect to t function. So 2 chain rule formulas. The first one formula, all right. The first one, partial f over partial s. 3 terms. Okay. First one, partial f over partial x. Oh, sorry, derivative. Yeah, df. df over. Sorry. Yeah. But actually, it's a partial. Yeah, it's not d. Right? Yeah. So I will change that, because only for one variable function you use d. Right? For multivariable function you use partial. Yeah. Because I think the reason I copied from there, so I forgot to change. Yeah. So I will update. Because to write it, f is a multivariable function, right? So we should use partial here, partial here. Okay? Partial here, partial here. Okay? All right. Yeah. Only, so here, single variable, this is a single variable case. We use d. Okay? Single variable, there is no partial. Yeah. So we use d. Yeah. All right. The second chain rule, we should also do the same thing. Yeah. The partial. Okay? All right. Yeah. Yeah. All right. Yeah. So that's give you these 2 cases. Yeah. That should be enough for us. Yeah. All right. Yeah. So let's, with this preparation, let's do a problem number 7. Rate of change of distance. Let's do one application question. All right. Yeah, so let's look at this diagram here. 2 persons climb the mountain. So this is a mountain, okay? Shape, mountain. Matthew and Jessica climb the mountain like this. So Jessica and Matthew running toward the point P. Yeah. Point P. The destination is P point. Along the straight paths that make a fixed angle theta. Yeah. Theta. Suppose that Matthew runs with velocity, this velocity, okay? Velocity VA, meters per second, and Jessica with velocity VB, meters per second. Yeah. But the velocity, it's not a constant. It's a function of t. Yeah. VA, VB, yeah. So it's a function of t. Yeah. So usually not a constant. Yeah. All right. Let f function, xy variable, represent the distance between Matt and Jess. Now, distance from Matthew to Jessica when Matthew is x meters from P, the distance between Matthew and the P. And Jessica is y meters from P. Yeah. So the distance between Matt and Jess, f of x and y. Definition of this function. All right. Then give the question. Determine the rate at which the rate of change, derivative, right? Rate at which the distance between Matthew and Jessica is changing when x is 30 meters, y is 20 meters, velocity VA equals 4 meters per second, VB equals 3 meters per second. Yeah. So at a certain point, there is one point, one specific point. These numbers are measured, okay? These numbers. Yeah. But now you need to calculate the derivative of this function, right? Yeah. What's the rate? The rate of the distance. This is distance function. The rate of distance with respect to time t. Yeah. T is the variable, okay? Time t variable. Yeah. All right. Because x is a variable of t, x is a variable of t. VA is a variable of t. Y variable of t. VB also a variable of t. Yeah. Yeah. So it's a t function. Yeah. Variable t function. All right? Yeah. We need to apply law of cosines here. Law of cosine. Let's review. In this triangle A, B, C, based on the law of cosine, we have a squared equals b squared plus c squared. A squared, that's a squared, equals b squared plus c squared minus 2bc times cosine of angle A. That's the law of cosine. Here you can see when we calculate f of x and y in this triangle, same situation in our law of cosine. Yeah. So we just calculate f function. Yeah. But because square, you take square root. See, square root. Yeah. X squared plus y squared minus 2y times cosine of theta. Yeah. But x is a function of t, y also a function of t, but the theta is a constant. Yeah. Theta never changes. Theta is a constant. Now, you need to calculate the rate of change df over dt, right? Yeah. df over dt. Yeah. All right. X is a function of t, y also a function of t. Yeah. But now you take df over dt. Because if you, in this f function, you replace x by a function of t, replace y a function of t, the whole formula is a function of t. That's one variable. That's, you take the derivative, that is df over dt. So it's not partial. Yeah? One variable function. So here, so we do not yet write partial f over partial t. So it's a df over dt. One variable case. All right. But when we apply the chain rule, we need to use partial derivative, right? Yeah. When we using, yeah, here, we need to apply the chain rule because this is a composite function, right? Composite function. X is another function, x of t. Y another function, y of t. So it's a composite function. Composite function, we need to apply chain rule. Yeah. All right. How to write a chain rule? Partial derivative with respect to x, the first partial derivative. Partial f over partial x times x prime of t. Yeah, that's chain rule, the first part. Okay? Yeah. The second part, with respect to y, partial f over partial y times y prime of t. That's the chain rule version. Yeah. All right. Yeah. Now, we are ready to calculate the rate. Yeah. So we're ready. Yeah. This partial derivative, you can calculate partial derivative of this one formula. Yeah. You can find the expression. And you plug in x equals 30, y equals 20, VA is the x prime of t. VA is the x prime of t. at a certain point. Yeah. So here, how do we interpret VA? Okay? Yeah. Because there is a specific time point. Yeah. So our interpretation, x prime of t0. Yeah. Yeah. We do not have the specific value of t0. So at a certain time point, yeah, some time point t0, yeah, we do not know. So what time? Yeah. Yeah. But not important. Yeah. Not important. T0. Yeah. So V B, so y prime of t0. Okay? Yeah. Yeah. All right. And both x, y at the same t0 point. Yeah. Then, when we calculate this expression, we can plug in, right? We have everything. We have all the values of all the quantities. Yeah. All right. Yeah. Here, I put it in the further explanation. Okay. The calculation. Yeah. So 1C, yeah, our further explanation number 1. Yeah. Yeah. So here, we can save a few minutes. Yeah. So we complete it. Okay. All right. Yeah. So that's problem number 7. Yeah. Then, C.3, second order partial derivatives. So let's, look at this topic. Yeah. Second order partial derivatives are the derivatives of first order partial derivative. So f sub y, x and f sub y with respect to x or y. Yeah. Here, let me write all the possible cases. Yeah. The first one, yeah, take partial derivative on x twice. Yeah, yeah, twice. Okay? All right. Yeah. So that expression. Then f sub double y, yeah, twice. Okay? Then the mixed version. So x once, y once, mixed version. Okay? There is another mixed version. Take partial derivative with respect to y first, then x second. Okay? All right. Yeah. But there is an important theorem. Yeah. Clara's theorem. Yeah. That tells us under certain condition, there is some condition. Okay? Under certain condition, they are the same. They are the same. Okay? So let's look at the condition. Equality of mixed partials under some condition. All right. What condition? If x sub xy and f sub yx are both continuous function on a disk D. Yeah, disk. Yeah. Yeah. So we consider this disk D, yeah, with the center at A and B. Yeah. Because here we look at the partial derivative at the AB point. Then we draw a disk D around the center D with certain radius R. Okay? Yeah. All right. So in this disk area, these two mixed partial derivatives are both continuous functions. That's the condition. Okay? Yeah. If you do not have this condition, then you don't have this equality of mixed partials. There is a counterexample. Yeah. Our textbook, not our textbook. Yeah. So you can find a counterexample. Yeah. So if you do not enforce this condition, yeah, at this AB point, these two functions not continuous, then you cannot use that equality. Yep. Question? Yeah, limit. Yeah, when because at that point you can approach to this point from different directions, right? Yeah, From one direction, your limit is one value. You approach from another direction, you get a different value. Then it's not continuous. If it's continuous, you approach from any direction, same value. That's continuous. Yeah, different direction, value different. Braking, jump. Yeah. So if it's not continuous, then you cannot apply this theorem. All right. Yeah. So then, if it's continuous, because most of the time it's continuous. Our function is pretty good most of the time, good enough. Yeah. So you can apply this property, equality. Yeah. All right. Yeah. Next, C.4, linear approximation of and tangent plane. Yeah. In one variable case, we have this topic. Now we want to extend it to, multivariable case. Multivariable, we also want to do linear approximation. How to do linear approximation? We use tangent plane to do linear approximation. One variable, we use tangent line to do approximation. Yeah. So here, tangent plane. All right. Yeah. So let me explain the basic idea. From tangent line to tangent plane. Yeah. Yeah. So we look at a one variable case. We call it linearization of f function at point A. Yeah. Linearization. Yeah. The original function is not a linear function. Yeah. But we want to do linearization locally around this point A. In a small interval around that point A, we do linearization. How do you do linearization? We take the tangent line. Tangent line is our linearization way. Yeah. All right. The equation of tangent line. This is the equation of tangent line. L of x, tangent line equation, equals f of a, that point, the center point. Yeah. The point as the center. Yeah. F of a plus the derivative f prime at this point A times x minus a. This is a linear function, but this linear function is very close to the original function when x is very close to a. When x is very close to a, so these two functions very close. If x is not close to a, then these two functions not very close. If I draw tangent line graph, you can see the idea easily. Yeah. Suppose f function like this, okay, a curve like this. Then you draw tangent line. This is tangent line, okay, and this is the point A. Yeah. X equals a here, this point, tangent point. Okay, all right. You can see when x is very close to a, these two functions, the values of these two are very close. Yeah. Very close to this point. If far away, then not close. Yeah. So the linear approximation is not good if x is far away from a. Yeah. Should be very close to a. Yeah. The closer, the better. Yeah. All right. Now we want to generalize this idea to multivariable case. Yeah. Here, let's just do two variable case. Yeah. Yeah. A little easier to understand. Tangent plane, yeah. Two variable case. All right. For the two variable case, let's look at the geometric meaning non-variable case. Tangent line, yeah, geometric meaning. Okay, yeah. I drew that graph. That's the geometric meaning. All right. Now, linearization of two variable function f of x and y at one point, AB point, is this time another linear function. Yeah. This time the linear function has two variables, x variable and a y variable. Yeah. Yeah. So we write it in this way. Yeah. F function at the center point. Yeah, because we consider the x, y values around with this as the center. Remember that disk, okay? With this AB as the center of that disk D. Okay. Yeah. You consider there is a disk around this AB point. Yeah. All right. So first, take the value of the center point. Then, partial derivative at this point, but multiply A minus A, x minus A. Plus another partial derivative at this point, center point, then you times y minus b. Okay? That's the, generalization, extension from one variable case. Yeah. So here you have the two variable case, and this is the tangent plane. Okay? It's a plane. Yeah. Yeah. This linear function in this two variable case, it's a plane. Yeah. All right. Yeah. Tangent plane. Yeah. Why tangent plane? Yeah. Let's look at the tangent plane. Yeah. The geometric meaning here. First, the point P, AB, and the value. Yeah, because you plug in the x equals A, y equals B, then this L function, L of AB equals F of AB. Yeah. So at this AB point, these two functions, L function and original function, they match at the AB point. Yeah. All right. This is the first property. This is the first property. Okay. All right. And the plane equation, z equals capital L of xy. That's the plane equation. Okay? Z. Yeah. All right. Yeah. Second property, this plane is unique plane containing the tangent lines to the two vertical trace curves through P. The first vertical curve, this vertical curve, trace curve, and a second vertical trace curve, and two tangent lines. First curve and the second curve. Let me draw the picture, because this case, it's not easy to see it. Yeah. I need to draw the 3D graph. Yeah. So x, y, z coordinates. Yeah. All right. So here. X, y, z coordinates. All right. Z coordinate, y coordinate, and x coordinate. Okay? All right. Then, look at this vertical trace curve. Now, how do you see this vertical? Because x is fixed. X coordinate is fixed. It's A. Y is a variable. So, z is a function of that y variable. Okay, all right. Now, in the x coordinate, this is A. Fixed. Okay? When you fix that, you can draw a vertical plane. Vertical plane. All right? So all the points, so here I need to draw this 3D version. Okay? Vertical. Yeah, vertical at this point. Then this plane, pretty hard to draw. Okay? Yeah. Vertical. vertical plane, okay, like that. Inside this vertical plane, you draw this curve. This is the vertical curve inside this vertical plane. Then there is a tangent line, okay? Tangent line of this curve, okay? AB point. Yeah. Similarly, this one, you fix that y value, another vertical plane, okay? Yeah. But you take the vertical plane, B, this place, you draw vertical plane, okay? The curve, tangent line. Yeah. So these two tangent lines, two tangent lines can determine one plane, right? That plane is the tangent plane. That plane. Yeah. A little harder to imagine. Yeah. Yeah. But that's the meaning. Okay? That's the meaning. Yeah. That's the way we do the generalization from 1D to 2D. Generalization. Yeah. Okay? All right. Second property. Yeah. Third property, we call the local linearity property. Local linearity. Local. How local? Small area around the center point AB. AB is the center, our focus point, yeah, the point of our interest, AB point. Okay, so we draw a small disk around this AB point, so that's the local area. Here, we need to consider local linearity of this original function, the f function. This f of xy, this function, does it have the local linearity property? Sometimes it has, sometimes it does not have local linearity property. So we need to take a closer look at this local linearity property. Yeah. In the 1D case, we also have this local linearity property. Then 1D case is very simple. If f prime of A exists, then it has the local linearity property. That's simple. F prime of A exists, the derivative exists, then it has the local linearity property. That's the 1D case. But 2D case, more complicated. More than that. Yeah. So let me explain the 2D local linearity case. Right. A function f of x and y is locally linear at this, yeah. Yeah, so it should be, because at this point, yeah. Yeah, put this point after at this point, if f function can be represented, the tangent plane equation plus some epsilon function. Epsilon could be determined later, but epsilon function times this distance expression. Yeah, the distance between x, y, and AB. The distance function times certain epsilon function, but the epsilon function has this limit. When x, y approaches AB, this epsilon function, the limit of the epsilon function should be 0. If f of x and y satisfy this condition, we say it has the local linearity property. That's the definition. Okay? Definition. But the question is, how do you know? Now, although you can calculate, yeah. So there are some examples you can calculate the epsilon function. Given f function, you can find appropriate epsilon function. Yeah. Said that has this property. So you can prove it has the local linearity. Yeah. But now we want to do it in another way. Yeah. Differentiability and linear approximation. Why local linearity property is important? Because we need that property, local linear property, to do linear approximation. If our f function does not have the local linear property, we cannot do local approximation. We cannot do linear approximation because the approximation will be very bad. Okay? So the reason we can do linear approximation, we need to make sure it has the local linearity property. That's the logic. Yeah. But how to get that? Yeah. Let me explain the idea. By definition, f of x and y is differentiable at this point. Yeah. So here, we need to look at this original function, two-variable function, is differentiable at this point. How to get that? How to see it is differentiable? How to determine f of x is differentiable at this point? Look at the condition. Partial derivative x, f sub x of AB exists. The second partial derivative also exists. Okay? Two partial derivatives must exist, but not enough. Okay? Not enough. Another condition, this f function must be locally linear at this point. Okay? Two partial derivatives exist, plus local linearity property. If you have these, because these two partial derivatives exist, it does not guarantee f function is locally linear at AB point. It does not guarantee. Okay? There is some counterexample to show. Yeah. So that's why we need that three conditions to make sure f of x is differentiable. Yeah. Because that's the definition of differentiable. Yeah. That's the definition. Yeah. That means these two conditions are equivalent. Okay? F function differentiable, this condition, and these three conditions adding together, they are equivalent. You can go both ways. Yeah. If f is differentiable, then you can go to that direction. Okay? Yeah. Locally linear. If you have those three conditions, then you can go back differentiable. Yeah. So two-way. All right. Now, remember our goal is we want to do linear approximation. So we want to have the local linear property. Before we apply linear approximation, we need to check if our function has this local linearity property. Yeah. But the question, how do you check it? How do you check if our given function is local linear at AB point? Okay? All right. Here. All right. This statement, this proposition, give us the simple way to check. If f sub y AB and f sub y AB exist and are continuous in a disk D containing AB. Okay? Continuous, yeah. Those two functions exist. Yeah, exist. And those two functions continuous. Yeah. 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 So here, yeah. Continuous. Yeah. Continuous. Yeah, because continuous, I think, yeah, you should understand what is continuous. Yeah. You need to go back to x and y. X and y. Yeah. Yeah. So the partial derivatives, but you should use variable x and y, two variables. Yeah. Yeah. Those two functions continuous in that disk D around AB point. Yeah. All right. And then f of x and y is differentiable at AB. Yeah. So that condition continuous in that disk. Okay. This partial derivative continuous in that disk. It's enough to guarantee that f of x, y is differentiable at AB. If it's not differentiable, There you have local linearity, right? Yeah. Yeah. But to check these two functions continuous in the disk D, that's easy, right? Yeah. That's easy. Yeah. So this result, we can use this result to help us check local linearity of the original function. Okay? All right. So the last few minutes, yeah. So I may, show you something. Yeah. All right. So the linear approximation. Now, after we have the local linearity property, we can do a linear approximation. Okay? This is the first version linear approximation. Okay? First version. All right. Second version, we use delta. This is second version. Delta, yeah, from the tangent plane. Yeah. How do you get both of these corresponds to that tangent plane? Okay, tangent plane. Yeah. All right. These two versions. Differential. There is a differential version. Okay. Yeah. These two approximate version. But the differential version, we use df, dx, dy. You can see that's the equal sign. That's the equal sign. That's because differential. Yeah. We take the limit. Yeah. Dx, dy approaches 0, there we get an equal sign. Okay? Yeah. So differential version. You can use the equal sign. All right. Delta notation. Yeah. So for the 3 variable case, the delta notation. Okay? All right. Yeah. Yeah. So that's, these two versions. Yeah. All right. Then the last one, I only want to because the last one pretty short. Yeah, pretty short. Yeah. So this cylinder, the volume of the cylinder formula, you can see this function is differentiable, right? Very easy to see, differentiable. Yeah. Then we have the local linearity, right? Yeah. Because if it's differentiable, then it must be local linear. Yeah. So we can do linear approximation. Here the question. We want to get percentage increase in V if R and H are each increased by 2%. Okay? Yeah. Calculate percent increase of the volume. Yeah. But you are given percent of increase of R is 2%. Percent of increase of H also 2%. But how much is the percent of the volume V increase? Here we apply linear approximation, because this is differentiable function. So we have the local linearity property. Yeah. So the differentiability, no problem. Local linear, we have it. So we can do linear approximation. Yeah. How to do linear approximation? We can take tangent plane. Okay? Our tangent plane formula. All right. Yeah. So the last, we can do complete quickly. Starting point, so this is our approximation formula. But we need to apply it on this volume V, so delta V. We write a similar delta V formula, similar to that. Partial derivative, okay? 2 partial derivatives. The partial derivative V sub R, very easy, right? Partial derivative, okay? Yeah. You treat H as the constant. You take derivative on R. Partial derivative on H, you get that. Okay. Now you go back to this one. Delta V approximately equal to 2 partial derivatives. Then volume increase delta V over V. That's the volume increase. Okay, percentage volume increase. Now you take, simplification. Equals these two. Delta R over R, 2%. Delta H over H, also 2%. 2 times 2% plus 2%. Answer is 6%. Yeah. So that's how you calculate linear approximation. Okay? Linear approximation. Yeah. All right? Yeah. Try to understand the logic. Yeah. Okay? Partial derivative linear approximation. All right, so let's stop.